Good afternoon, Riverwatch folks. Megan McConville here, and today's Zoominar, we're talking about 30 years of Riverwatch data, which you guys have all contributed to. But kind of the title and the goal of this Zoominar is to describe a little bit of the black box of what happens when you collect your metals samples and then send them to us. How do we actually analyze them? So this will take us into the Fort Collins lab, and not specifically. So in April, we're destined to get a new instrument, so an ICP-MS spec. And we hope that at that point, we'll be able to actually show you the lab and the working environment, which right now is being remodeled to have capacity for that new instrument. All right, so when we think about priority pollutants in Colorado, and you guys probably remember this from trainings or maybe from your work and with your teachers, but the primary pollutants in Colorado are metals, and that's from our historic mining history, as well as sediment, and shown there on the right, you know, Glenwood Canyon post fires this past summer. Sediment can be a really detrimental pollutant to streams because it suffocates, you know, macroinvertebrates or bugs at the bottom of a stream, making it really difficult for fish and other aquatic life to find that food. So it actually suffocates or fills those little spaces between rocks where macroinvertebrates make their living and exist. Nutrients are another big pollutant in various other states. In the United States, nutrients are, you know, higher up on this list, but a growing problem because of point and non-point sources that deliver nutrients in excess amounts to waterways that then leads to the proliferation of algal blooms. And you can look back at a previous Zoominar where my colleague Ashley Russ talked about some of the cyanotoxins. But today we're gonna focus on metals. So you guys fill your sample bottles, a filtered and a non-filtered sample, and we analyze them for these 13 different metals. And so aluminum, arsenic, calcium, cadmium, copper, iron, potassium, magnesium, manganese, sodium, lead, selenium, and zinc. And part of the reason that we have selected these 13 is because they're commonly found in waterways throughout Colorado. Some of them are trace metal contaminants that acutely impact fish and aquatic life, like cadmium or copper or lead. And some of them, like calcium or sodium or magnesium, those represent the cation or the positively charged salt fractions. These images show kind of a famous Colorado story of the Animas River pre and post a mine spill. So we were looking at metals contamination from a spill from an abandoned mine. The one on the right is an area on Lincoln Creek above Aspen and the Roaring Fork drainage, again with old mining activity. So in all of these cases, these metals provide a clue as to what's happening in various watersheds throughout Colorado. So again, today's focus is going to be on the instrumentation that we use to analyze your metal samples. And for over 20 years, we've used the instrument here on the left, an ICP-OES. So ICP stands for Inductively Coupled Plasma, and I'll talk a little bit more about what that actually means. And then OES is an optical emission spectrometer. And this April, we will be obtaining a new ICP inductively coupled plasma, but mass spectrometer. So in each of these, the start and how the sample gets introduced is the same, but the detector is different. One way that I like to think about these is the OES, or the optical emission spectrometer, is more like our eye or a camera lens, where we're actually picking up individual light, or how a camera lens, like different intensities of light and different frequencies that represent maybe different colors, versus a mass spectrometer has this ability to very accurately measure minute differences in masses, like isotope differences, or in this picture, right? Like subtly a slightly different feather, or, you know, we cut a few of those particular feathers off of that feather. I'm not describing it well, right? But if we were to reduce that mass just a little bit, this mass detector could, or this mass spec could detect those minute differences versus the rock. So maybe we see salt as the rock in a river, these high concentrations, but similarly in the same breath and in that same sample, we want to see really minute concentrations of, say, copper or lead. Okay, so how does an ICP optical emission spectrometer work? This one that we've been using for 20 years, which has been a power horse and you know, something we've relied on and has given us excellent and accurate data. So again, think camera lens, or kind of the way our eye works. If we think about electromagnetic radiation, right? And maybe this part right in the middle, the part that we all think about a lot, is the visible range of light, from red to orange to yellow to green to blue to indigo, the forgotten color, to violet, and then kind of this ultraviolet spectrum. This big oval represents what an optical emission spectrometer relies on. And then you have, right, radio frequencies, those like longer wavelengths up to like gamma rays or X-rays. Think about, you know, getting an X-ray on your tooth, or you break your bone. Those are much higher frequency wavelengths. But again, the region that we're looking at for an optical emission spectrometer is kind of what our eye can see, which again is that relationship to an eye or to a camera. Okay, on both instruments, we take your liquid sample, right, your metals bottle, we insert basically a straw into it, and we transform your liquid sample into a vapor. And we do this by heating it up, basically, or kind of moving and creating a vapor. In the optical emission spectrometer then comes through this little, it kind of looks like a pencil on the end here. This is a center tube, and then this is a torch that is able to sustain super, super high temperatures. Then we are creating a plasma, or basically the sun inside this instrument. So this sun allows these elements, copper, magnesium, sodium, to be atomized and ionized. And during this process, as these elements get excited, they emit light. And they emit light at known and specific frequencies or wavelengths. Some of that light is better detected in what's called this axial direction. So it goes in line kind of with this center tube across the picture here. And some of them are radially. So there's like a little hole down here, and you're actually detecting it this way. So axially and radially. So these atoms and ions emit light at these known and specific frequencies, and each one has kind of a unique fingerprint. Basically, we have all of this incoming light, and then within this detector, we are separating it into these known wavelengths and frequencies. So here's our red and yellow and orange and blue and green and all of those different colors. And then we also get that ultraviolet spectrum and scale. And through a series of mirrors, we are focusing that beam into known places on our detector. So that's how this instrument works. Here's a periodic table. Maybe you've seen this before, but this is the emission spectra of all of these different lines. And as you can see, this may look like a jumble, but here's hydrogen, right? Like these frequencies or the intensity of the light at these different wavelengths is really different than what it looks like for sodium, which is different than what it looks like for copper or for zinc. And these are the fingerprints that we're able to quantitatively identify what happens in your sample, or the concentration of zinc versus the concentration of copper. Okay, so this gets into a limitation. So that's kind of the basic premise of an optical emission spectrometer. And I'd be happy to invite you to the lab, and you could come and we could talk about this in more depth. but why are we moving from this instrument that has been the workhorse of the Riverwatch program for a couple decades? And one of the main reasons, and I know this slide is busy, and I only ever put up busy slides when I can talk about them specifically, is here's our 13 elements across the top, and then here's the current Riverwatch method detection limit. So the lowest concentration that we feel confident we can say is different than non-detect or not present in our sample. So these numbers are generally pretty low. But hopefully your eye was caught on these red ones, right? And basically those indicate that the minimum detection limit, or this one, the reporting limit of our laboratory, is higher than the chronic state standard. So this is a standard based on aquatic life that we've indicated we see an effect on aquatic life when cadmium is present at 0.13 micrograms per liter, or part per billion. Really, really small concentration, but we see an effect. And our reporting limit for Riverwatch is not low enough to account for those very low impacts we see. And that's reflected in these chronic or low concentrations over a long period of time that build up, or these acute state standards, meaning that if there is 0.67 micrograms per liter of cadmium present at certain hardness concentrations, acutely you can kill certain aquatic life. Okay, I'm gonna pause there and ask Noah and Christine and Bradley, who are on this call, if they have any questions.
I guess I have a question. What is the difference? You're showing the OES. Is there a table we have for the mass spec that we're getting that would show what the reporting limit is for those, or is that coming up?
It's coming up. Thank you, Bradley.
Cool.
Christine was shaking her head, no questions at this point, but these are these critical pieces that we run annually to say, we feel confident that this is a level that we can accurately detect on our instrument. Noah, you had a question?
Yeah, a few slides ago. What does it mean when you're heating up our samples for it to be like iodized and atomized? Was that the terms?
Yeah. Yep. Ionized and atomized, right? So we're creating ions, so charged particles. Basically, every atom, when you heat it to a certain frequency, there are these outer shells of electrons, right? At some point in your courses, you maybe have gotten there or you may get there, but there's this excitation of these electrons, and these outer electrons actually leave, creating instability in your source. So you're actually giving them a charge. So an ion is a charged particle, and those charged particles emit more light. So we want to create individual known ions that allow us to kind of see or know the concentration of these different elements and what's in your metals bottle. Does that help?
Yeah.
Yeah, but there's a small little sun. Like this gets hot. We have to have a chiller to keep everything else cold. We are creating a small sun inside this instrument, which is really amazing. So it's an incredible technology.
Is it one temperature, or does it vary depending on which atoms you're trying to excite?
That's a great question. Generally, this is at like 3,000 to 5,000 degrees C, right? Like so hot, right? Bradley's eyes are getting really, really big. There is some modulation that happens, but we are using a gas to create this plasma source. And we're using electromagnetic radiation. So around this radio frequency coil, we are moving energy so quickly, and gas molecules are attracted and start moving and colliding. And this creates this plasma gas. All right, so what about an ICP mass spec, right? So how does this mass spec work? And hopefully we've presented what our challenge is. This doesn't mean, these red dots don't mean that any of our data is bad. It just means we want the capacity to be below these standards so that all of your data continues to be relevant for decades and decades into the future. We want to make sure that we are able to detect concentrations that impact aquatic life. Okay, so mass spec. Again, these are, we're going to show you down the road, these fit on a benchtop. They're not huge, but the capacity and what they're doing inside is really robust and exciting. Again, so we're looking at mass, so not this optical side of things, not that visible spectrum. We're looking at minute changes in this little feather, right? I snip off a few of those, what are they called? These little parts of the feather. You guys are thinking about it. Okay, you snip off a few parts of that, right? And you get a slightly different mass. And accurately, I can measure that rock simultaneously to that feather, or a few snips off of that feather, or just the tiny, tiny ones, right? And these represent obviously much smaller masses than this, you know, image can relay. Okay, so similar, right? We are creating a liquid sample. Now on this side, it's coming in the same direction. We're vaporizing that sample. It goes through this new instrument we're gonna have. Instead of this radio frequency coil, this is a patented device called a Luma coil, which is amazing. Again, plasma is created. Elements are atomized and ionized. They then make their way through this triple cone design, the idea being to avoid interferences, to get rid of, you know, sediment that comes along with your sample, right? I know each one of you have sent me a bottle that is very full of sediment and one that's not. And so we're trying to decrease those interferences and not let them reach this really expensive and high precision detector. Okay, so vaporized and ionized, again, plasma, right? Sunshine, 3,000 to 5,000 degrees C. And then what's really amazing, this goes under a vacuum. So inside this vacuum, basically we reduce gravity. And we're able, through different charges within this universal cell, to direct these unwanted or neutrals, things that don't have a charge on them, or total suspended solids, right? All in one line. So those go away from the detector, and all of these ions, let's say the red is sodium, let's say the yellow is lead, let's say the green is copper, right? We are moving those ions in a directed path that actually turns a 90-degree corner. Amazing. Okay, so then they go into this cell, and the cell has these quadrupoles around it. Again, what do we say? Red is calcium, yellow is lead, green is copper. And within this cell, we are then able to get rid of additional interferences. And there's 3 different modes that we can operate this in. There's the standard mode, there's a collision cell, and there's reaction cells. So this is where the chemistry, the physics get really exciting and really interesting, but this allows us to reduce our method detection limit really, really significantly. Then it goes into this analyzing quadrupole. So again, quadrupole meaning 4 of these rods, basically. And in this analyzing quadrupole, basically we line things up. You're getting in line for the drinking fountain, you're getting in line to go outside, and we are lining up these ions based on their mass and their charge. And so then they reach the detector. So it's a way to determine what is coming out and in what order. And of course, this is happening so quickly. You know, this is a much slowed down version of what's occurring. Okay, periodic table again, right? So this time we're looking at different isotopes. Isotopes meaning if you have your molecule and you take off 1 proton, right? That mass is changing so subtly. This is my analogy with the feather, that it doesn't take much and yet we can detect those individual differences. So let's look at zinc, right? Zinc has 4 stable isotopes that are naturally found. And this instrument can identify one versus another, right? So you can see that 64, zinc 64, this highest abundant peak, that's present in a higher amount universally than zinc at 66, that next line. 67 is really small and 68 after that, or maybe 5 stable isotopes, maybe I'm missing one in there. But these minute differences is what this mass spec can detect and distinguish between. Okay, so what impact will we have? Coming back to Bradley's question, what do we expect the minimum detection limits for our mass spec? So I'm showing the same chart, but now we add this anticipated lower detection limit for the mass spec. And I had to change the font size, right? We go 3 to 5 orders of magnitude smaller. So our current Riverwatch minimum detection limit for aluminas is 4.6. This instrument has the capacity to go 0.000, we're at part per trillion already, 0.01. Let's look at the one we were looking at earlier in a little bit more detail was cadmium, right? We go from 0.3 down to 0.00006 micrograms per liter. So again, the ability of us to continue to be relevant in the data that you are all collecting is what this instrument will give us capacity to do. I focused in on a few of these because that last slide was really small. So again, just this anticipated method detection limit. And what's also really unique, if I scroll back one slide, you know, we're able to see magnesium, which we expect to be present in really high concentrations, milligrams per liter, you know, what you could actually see, you could weigh out on your balance or your scale at home, maybe what you put on your toast or your pasta or whatever it is to make it more salty, that sodium or magnesium component, things that you can visualize, versus these part per trillion concentrations. That's, if we had 1 trillion people, it would be one person in that trillion. That's kind of where we get with these numbers. All right, so that's a small snippet of the differences in these two instruments. Again, open invitation for anyone to come to our lab. We hope to have the new ICP mass spec installed this April. There'll be some startups, some initial quality control testing that allows us to switch from the optical emission spectrometer to this mass spec and continue to analyze your data. But our goal always is, if you're taking the time in all months of the year to collect this data, we want it to make a difference. So I'm going to open it up to questions at this point, or any other points of clarification, or if anybody knows what a small bit of feather is called.
I don't know what a small piece of feather is called, but I had a couple questions. I thought you explained it really well, but what would be like, are there any downsides to switching over to this new ICP? Like seems to be more accurate or whatever. Is there any downsides? Like maybe we have all this historical data using the same technology. Would that be a downside switching? Is it going to change anything going forward?
One of the differences in what we've been trying to do critically with Riverwatch data is when lead is not detected in your sample, it doesn't mean that it's not present. And so your reporting may show 0, but 0 is never really 0. It's just the ability of our detector to quantify what may or may not be present. So the biggest change that I anticipate is we have been really confident in analyzing, a higher portion of concentrations. What we will do with the mass spec is basically increase that lower end of our spectrum. So I don't anticipate, if you've had sodium at a concentration that this optical emission spectrometer has routinely measured, that the mass spec will be able to verify and get very consistent results. We will also do some testing at the beginning with samples from different parts of the state and look at them on the two instruments and do a cross comparison to verify that there are no issues. But really the biggest piece that's going to change is we're going to lower this bottom end, but the top end will still be able to have really representative data across the picture. So where before you never saw any cadmium, you might see it at these really, really, really low concentrations. But again, that's where the standards come into place. Either those acute immediately create issues or problems or death, or those chronic ones where it builds up over time. Those standards are critical because even zinc at low concentrations is an essential nutrient. So it doesn't mean that all of a sudden, if your river has some zinc in it, it's necessarily a problem.
You answered my other two questions there. Another one I had was, on your previous slide, you had expected reporting limit for this new mass spec. How are you going to go about calculating that and getting like a current, like how do you calculate the reporting limit?
Awesome. So there's a specific methodology that I follow that the health department and EPA has built and verified. And basically what I do is I take really small known concentrations of all 13 of our elements. And on successive days in the lab, so you get that fluctuation, it's a cold day, it's a warm day, how do we find consistency in what the instrument can do? And so I measure those routinely. I want 10 samples back to back to back to back of these really low concentrations. And I do that on 3 successive days with different solutions that I make up each time. So there's not that caveat that maybe one day as I'm preparing those solutions, I've done it differently. The idea is that you have fresh solutions each day and you build in what may be expected as you're preparing for analysis. Then there's different mathematical formulas that we're putting this in basically to look at the standard deviation and how close we are to an expected concentration. So this is something that we've been performing in Riverwatch annually, which is the cycle suggested by the health department and EPA. So we follow that methodology and we'll do the same with this new instrument. All right.